The State Route 71 Blackbird could fly above Mach 3, yet on the ground it could sit there dripping fuel. The popular explanation is that engineers deliberately left the tanks open, knowing heat would close the gaps later. That is almost right, but it turns a difficult sealing problem into a clever party trick. The real question is not why anyone wanted the airplane to leak. It is why they could not make one seal work in both the cold airplane and the hot one. At sustained Mach 3, air rubbing and compressing around the Blackbird heated its skin and structure. NASA used the aircraft for thermal experiments that produced heat-soaked temperatures above 600 degrees Fahrenheit. Aluminum was a poor fit for that environment, so the airframe was built mostly from titanium and titanium alloys. Titanium tolerates heat well, but it still expands. The airplane that landed hot was physically not quite the same size as the airplane waiting cold on the runway. The fuel was not stored only in removable containers. A contemporary technical account describes 6 integral tanks built into the fuselage. In an integral tank, the aircraft's own structural panels and joints are part of the tank wall. That saves weight and space, but now every seam has 2 jobs: carry aircraft loads and keep fuel inside. When the structure flexes, heats, cools, and changes shape, the fuel seal has to move with it. Picture one tank seam while the airplane is cold. The metal panels have contracted and the sealant bridges the joint in that cold geometry. During high-speed flight, the same panels expand. Slip joints let parts of the airframe move instead of buckling, while the sealant stretches and compresses across the changing seam. In the hot state, the tank geometry tightens and a leak path can close. After landing, cooling reverses the movement, and the entire seal must survive the trip back. This is where the phrase "designed to leak" becomes misleading. In a declassified paper, Kelly Johnson wrote that Lockheed spent years developing a fuel tank sealant that did a reasonable job from -90 degrees Fahrenheit to above 600. Another development record lists fuel tank sealant life at high Mach temperatures as a significant problem. Those are not descriptions of an intentional open hole. They describe a material being asked to remain flexible, fuel-resistant, and sealed across repeated extreme thermal cycles. The sealant and joints were good enough to operate, but not perfect in every state. A 1981 first-hand account says repeated skin heating in flight and cooling on the ground made the tanks impossible to keep fully sealed, and describes substantial fuel pooling beneath the aircraft. Crews managed that leakage as an operational and maintenance problem. The important distinction is simple. Engineers tolerated the leak because of the larger thermal design problem. The leak itself did not help the airplane fly. Once the Blackbird accelerated and heated, the airframe expanded toward its high-speed operating shape. NASA's explanation is unusually direct. On the ground, the tanks leaked, and they did not seal until the aircraft heated up in flight. That does not mean every drop stopped at exactly one temperature. It means the hot geometry was the geometry the machine had to sustain at Mach 3, and the fuel system worked better once the structure moved into it. So the famous puddle was not a brilliant feature hidden in the fuel system. It was evidence of an aircraft stretched across 2 very different physical states. Cold on the runway, its integral tanks and sealant could leak. Hot at speed, expanding titanium tightened the same structure. The impressive part was not that the State Route 71 leaked. It was that one airplane could repeatedly heat, grow, tighten, cool, and shrink, and still return ready to do it again.